Welcome. The topic we will be discussing in this lecture is cache replacement algorithms. So in the last class we have discussed the mapping functions. What are the different ways of mapping the main memory with the cache memory? So we have discussed basically three techniques. One is direct mapping, the next is associative mapping, the third one is set associative mapping. The topic of today's class is like if the cache is full, assume the cache is full, and now we want to bring a new block from main memory to the cache. So any one of the block from the cache memory should be removed so that a room will be created for the new block. So the crucial question is which block of the cache memory should be removed to bring the new block from the main memory to the cache. This is very crucial decision because this is going to affect the performance of the computer, right? So what are the different strategies available to deal with that, and how to do that? That's what we are going to discuss. Okay. So coming to direct mapped cache. So if you are using direct mapped cache, the positions of the which block of the main memory should occupy which block of the cache memory, that is predetermined. In case of direct mapped cache, the position of a particular block that will be occupied in the cache memory when you move a particular block from the main memory to the cache memory, at what position it should come, that is already predetermined. Okay, because we just divide the particular block number by the maximum number of the block available in the cache, and whatever the remainder to that particular block only it is supposed to go. So in this case we cannot apply any replacement strategy because you have to this particular block, for every block a particular block is fixed in that particular cache. Okay, so you have to replace only that, right? There is no other option. Okay, so there is no such replacement strategy exist for direct mapped cache because the position they occupy are predetermined, right? Okay, the replacement algorithm then it is applicable only for associativity cache and set associativity cache. Here we have some flexibility or some control to to decide like which block should be replaced so that performance can be improved. Fine. Okay. So the new block should be brought into the cache, and the question is when if the cache is full, if the cache is full, then any one of the older block in the cache should be removed so that the new block can come in. Okay, so the cache controller will decide like which block of the cache should be removed. Okay, so some older block should be removed or it should be overwritten. So which block should be taken out? So this decision is actually a crucial decision. So how we are going to identify? There may be many old blocks, but that doesn't mean that we can just like that throw away the old blocks because it may be immediately required by the processor again. Then in that case it will have a heavy blow on the performance. Okay, so it is an important decision to decide the right block to overwrite or to replace. Okay, because this is going to affect the performance of the CPU very much. Okay, so our objective is to keep such blocks in the cache memory which are highly likely to be referred in future. Okay, so the objective is to keep such blocks in cache memory which are highly likely to be referred in future. Okay, so you can only overwrite a block or you can only replace a block which is highly unlikely to be referred in the future. Okay, but how we will identify that whether a particular block is going to be referred in the future or not? How do we know that? That's not an easy decision. Okay, that there is no easy way to understand whether a particular block will be used by the CPU in the future or not, because we don't know about the future. The program may be given anyway. So here the concept of locality of reference may help little bit to devise some strategy for replacement. Okay. So the concept of locality reference, what it says that there are two things, temporal locality and spatial locality, right? So the temporal locality of reference says that whatever the block which you have recently accessed, it is highly likely that you will access it again. Okay. And whatever the block which you have recently accessed, it is highly likely that the neighboring blocks also may be referred by the CPU in the near future. Okay, right? So what's the best thing we can do is, it is sensible to overwrite a block or to replace a block which is not referred for a long time. Okay, not referred means not referred by whom? By the CPU. Okay, if a block is not referred by the CPU for a long period of time, so say the cache contains many blocks, then and the cache is full, now we have to bring a new block from main memory to cache memory. Okay, from main memory we want to bring one new block to the cache memory. So the question is, which block in the cache memory should be overwritten? So we have to identify such block which is not referred for a long period of time. So that is the best thing we can do. So identify the block which is not referred for a long period of time and replace that or overwrite that. Okay. So here, see, we are saying which is not referred for a long time. It is not the oldest block. See, for example, say this block came at time t0. That is the time first it came. Okay, the oldest one. And this block, it came at time t1. Say this block, it came at time t2. Okay, say this block came at time t3. Okay. Now say that even though this block has came at time t0, right? It was recently referred at time t2. It was referred. Okay. At t2 it was referred. Okay. In that case, the block which is not referred for a longest period of time will be t1. Right. So it is not that always the oldest block will be the one which is not referred for a long time. Okay. It may be any block. Okay. The block which is untouched by the processor for a long period of time is the one that is to be replaced. Okay, so that argument is quite sensible. Okay, fine. So replacing such a block, replacing a block which is not referred for a long period of time, that block is called as LRU block. Okay, that is least recently used block. It is least recently used block. Okay, the block which is not referred recently is called as least recently used block, and the algorithm that replaces such a block is called as least replace LRU replacement algorithm. Okay, right? The block which is not referred recently is called as LRU block, least recently used block, and the algorithm that replaces such a block is called as LRU replacement algorithm, least recently used replacement algorithm. Okay, so LRU stands for least recently used. Right? Okay. So let us see how LRU algorithm is going to work with set associative cache. Okay. So already we have discussed that the replacement algorithm cannot work with direct mapping. Okay, because there is nothing to replace, because uh, it is always going to map to the same locations of the cache or the same blocks of cache. Okay. So let us see for set associativity cache. So let us assume that the cache is divided into several sets. Okay, the cache is divided into several sets, and each set contains 4 blocks. Okay, so in a set there are 4 blocks. Okay, so when you refer a set, there are 4 blocks. Okay, so let us say 1, 2, 3, 4. This is one set, means this is set 0, means it has 4 blocks. Block 0, block 1, block 2, block 3. Okay, like that there may be another set. Another set. This may have another 4 blocks. 1, 2, 3, 4. Okay, right? So it has another 4 blocks. Okay, right? So you recall how the set associativity cache works. So we have discussed in case of set associativity cache, last class we have discussed that each set will have 2 blocks. Okay, each set will have 2 blocks. Okay, and the cache contains totally 128 blocks. If there are, if each set contains 2 blocks, and if there are totally 128 blocks, then totally there are how many sets? Totally there are how many sets? There are 32, there are 64 sets. There are 64 sets. Okay, so whenever you want to move a particular block from a main memory, say you want to move the block 120 from the main memory, block number 120, then you have to divide by 64 and find what is the remainder. That is, you have to perform modulo division by 64 and you have to find the remainder. Okay, because you have to identify to which set it will go. Okay, so 120 modulo 64, what is that? 56. Okay, so 120 modulo, so you have to perform modulo division 120 modulo 64, right? Because totally we have 64 sets, so the result is 56, right? So it will go to block 56, right? Is it clear? So it will go to block 56. Okay, but again if you see block 56, each block contains two, sorry, it will go to set 56, not block 56, it will go to set 56. Again in set 56, so if this is set 56, this set contains 2 blocks. Okay, so it can go to any one of these 2 blocks. It can go to any one of these 2 blocks. Okay, similarly here we are saying that one set contains 4 blocks. Okay, so let us assume the same case, like cache contains totally 128 blocks. 128 blocks. Okay, if each set contains 4 blocks, then totally how many set we'll have? So the number of set will be equal to 128 by 4. Okay, so the number of sets will be 128 by 4, which is what? 128 by 2. So the number of sets will be 128 by 4, so which is 32, right? So there are totally 32 sets now. So now we have 32 sets. Okay, because each set contains 4 blocks. Okay, now if you want to move a particular block from main memory, say this block 120 you want to move to from main memory to cache, now you have to modulo divide by 32. So 120 modulo 32 will be what? 120 modulo 32, you have to take the remainder, it will go to that particular set. So 120 modulo 32, the remainder is, okay, whatever the remainder it may be, right? So say let me 120 modulo 32, let me calculate, the remainder is 24. Okay, the remainder is 24, so it will go to the particular, it will go to set 24, it will go to set 24. Again in our case the set 24 contains how many blocks? We are discussing 4 blocks. Okay, so if this is set 24, if this is, I will call it as S24, set 24, it holds 4 blocks. Okay, 1 2 3 1 2 3 4. Okay, right? So I'm not recalling the same thing, I'm trying to connect with replacement algorithm. Okay, so it should come to set 24, right? Okay, now assume that all these, the set 24 contains 4 blocks, right? Assume that all these 4 blocks are full. Assume that all these 4 blocks are full. Okay, now what the memory controller should do, it should replace one of the block. It should replace one of the blocks so that this new block can come in, right? So it should replace which block? It should replace the one which is not used recently. It should replace the block which is not used recently. How we are going to find that? That is the question. Okay, it should replace the block which is not used recently. For example, if this is the block which is not used recently, then the new block will be overwritten here, or it will be replaced. Okay, replaced in the sense this block will go back to main memory and a new block will come here. Okay, but how we are going to do that, exactly the logic, how it is going to work, that's what we are going to discuss. Okay, so we are going, so the set contains 4 blocks, so some block from the main memory you want to move to the cache. So in this case, if you assume that each set contains 4 blocks, and if the total number of blocks available in the cache is 128, okay, then there will be totally 32 sets. Okay, so whatever the block number from the main memory we want to move, that you have to modulo divide by 32. Then whatever the result you get, whatever the result we are getting, to that particular set only this block should be moved. Okay, this block should be moved. In that set, if already there are some empty blocks, in that set will have 4 blocks, not more than that. 1 2 3 4. If there are some empty blocks, obviously this new block will go into that empty block. Okay, the problem comes when there is no empty block. Okay, when there is no empty block, we should identify the one which is not used recently and we have to move it out. Okay, so that the new block will come here. Now we have a question like how we will identify which is which is not recently used, which is recently used. So how we are going to do that? For that we are using a counter. For that we are using a 2-bit counter for each block. In our case, each set contains how many blocks? 4 blocks. Okay. So for each of these 4 blocks there will be a 2-bit counter. Okay. So let us assume each set contains 4 blocks, which are block 0, block 1, block 2 and block 3. So in each set we have these 4 blocks. Okay, so there will be a 2-bit counter in each block. Okay, so the 2-bit counter can hold how many values? It can hold maximum 3 values, 4 values, that is from 0 to 3. It can hold values from 0 to 3, that is 0 0 to 1 1, right? Totally 4 values, 0 0 0 1 1 0 1 1. Okay, like that all the 4 counters can hold values between 0 to 3, right? So in binary it is 0 0 0 to 1 1. In decimal we can say it is 0 to 3. Okay, right? So each of the counters will hold any one of these value. Either it will be 0 or 1 or 2 or 3. Now what is the meaning of that? See, if any one of the counter is holding the value 0, it means that block is used recently. Okay, the minimum value refers that if the value in the counter is less, it means that it is used recently. If the value in the counter is more, it means that it is not used recently. Okay, so if it is 0, then it means that it is very recently it is used. If it is 3, value in the counter is 3, means it is not used for a long time. Okay, if it is 1, means it is quite recently used. Okay, if it is 2, means it is somewhat, it is almost not used for a long time, but it is not worse than 3. Are you getting right? Okay, so for example, if all blocks are full and if this is the numbers, block 0 is I mean the bit 2-bit counter value is 0, this is 1, this is 3, this is 2, then which block should be replaced? Actually this block should be replaced. Okay, the one with the highest value should be replaced. The one with the highest value should be replaced. Okay, because that is the one which is not used for a long period of time. Okay, fine. So with this understanding, let us see how things works. Okay, so there are totally 3 cases we have. Case 1 is CPU want to access some content. Okay, CPU want to access some content and that content is already available in the cache. So that is called as cache hit. CPU want to access some content and that content is already available in cache. Okay, in some set of the cache it is available and each set contains 4 blocks. In that case, what should happen to the counter values? Okay, so if CPU is trying to access this particular block, okay, and if that block is available in the cache, then the counter for that block will be made to 0. Okay, whatever the block CPU is accessing, because this is the one CPU want to access, so this is the one recently accessed, so its counter will be made to 0. Okay, and all other counter values which are less than the referenced one will be incremented by 1. Okay, right? Previously this was what? 1. Okay, previously this was 1. Okay, is there any other counter which is less than this? 0. This is less than this. Okay, so this previously this is 1 and this is 0, so this will become now 1, this will become 1. Okay, other counters will be left unchanged because already they are more than this. 2, this is already 2, this is 3, so you won't touch that. Are you getting? So if there is a cache hit, okay, whichever the block processor is accessing, that block's counter will be set to 0. Other counter values which are less than the referenced one, okay, which are less than the original referenced value, that will be incremented by 1. Other counters will be unchanged. Okay, this is the case for catch hit. Okay, if there is a catch miss, in catch miss there are two cases. One is catch miss and there is a space available in that particular set. Okay, that means not all the 4 blocks are filled, some blocks are empty. Okay, so there is a catch miss and the set is not full. In that case, what you should do, there is some empty blocks, so just load the block from the memory to the cache. Okay, a new block you want to bring, but there are some empty locations available in the cache memory. Okay, you want to bring a new block from the main memory to the cache. Okay, and it obviously it will map to any one of the set. Okay, so the block number you have to divide by 32, so that will give you the set number. Now this set contains 4 blocks. Okay, so now the case 2 is all blocks, some, not all set is not full. Okay, that means some empty blocks are there. Okay, say 1 2 3 4, say 2 blocks are empty, this is empty, this is empty. Okay, now this new block can come either here or here. Okay, that is not an issue, there is no question of replacement. All these two are empty, it can take any one position. Okay, so after taking that position, the counter corresponding to this particular block, this new block is moved here, right, that the counter corresponding to that block will be set to 0. Okay, and all other blocks counter, okay, and all other counters and all other blocks counter will be incremented by 1. For this block the counter will be incremented by 1. For this block also the counter will be incremented by 1. In our case, this block, we assumed it is also empty, so there is nothing, right? Okay, so if there is a catch miss and the set is not full, then just load the block from the memory to the cache. Okay, and set the counter to 0 and set the counters for other blocks, and increment the counter for the other blocks by 1. Right? This is second case. Third case is catch miss. There is a catch miss, but none of the blocks are empty, all blocks are full. So this is the crucial one. So third case is, this is the one where replacement algorithm comes into picture. So third case is 1 2 3 4. So all the blocks are filled. So this is one set. Okay, but in this set all the blocks are full. There is nothing is empty. Everything is full. Okay. Now you want to bring a new block from the main memory to cache memory. You have identified a new block, and that block should come to cache memory. So now, but there is no empty space. So now it is very much required to replace any one of the block. Okay, so which block we will replace? The algorithm says that remove the block whose counter value is 3. So check the counter value for all the blocks. So we have a counter here, say this is counter 1, counter 2, counter 3 and counter 4. Okay, if there is a block with counter value 3, so counter value 3 means it is not recently used. Say for example, for this block the counter value is 3, then replace this block. Okay, so it means the new block will come here, that's it. Okay, and increment other counters by 1. Replace this block and increment other counters by 1. Okay, all the other counters will be incremented by 1. So this is how this LRU algorithm works. So based on this counter, so this counter actually acts as the tool to identify which is used recently and which is not used recently. If something is if something is used recently, then immediately we will make counter as 0. Okay, so whichever is not used, then accordingly we are incrementing the counter. Okay, so this is the whole strategy of LRU algorithm, right? Okay, so LRU algorithm is an extensively used algorithm. Generally it performs well, but there are certain situations under which it may not perform well. It shows poor performance, especially while accessing arrays of size which are slightly larger than the cache size. Okay, it means your entire array cannot fit in the cache, only part of the array can be placed in the cache. Okay, in that case the replacement of this LRU algorithm performs poorly, right? Because there may be a lot of swapping going on. It may not be able to identify the right element to replace properly. Or you can say that as you are accessing the element sequentially from the array, okay, as you are accessing the element sequentially from the array, uh, you may you may be immediately requiring the element which is moved out of the cache, okay. So then getting that from the memory again, it will become a costly operation, okay. So other than LRU, do we have any other algorithms? Yes, there is another algorithm which says that remove the oldest block from the memory. So whenever you want to replace, you replace the oldest block, okay. So LRU is not asking us to replace the oldest block. It is asking to replace the one which is not used recently. Whereas this second algorithm, it says that remove the oldest block, okay. So this is, otherwise you can call it as FIFO, first in first out. That is, remove the block which came first, okay, right. So uh, so right, so set is right. So I mean, so when the set is full, we have to replace the one which is the oldest one, right. But the problem with this algorithm FIFO is actually it does not performs better than LRU, right. It is not as effective as LRU because it is ignoring the pattern in which the blocks are accessed, okay. See, some block may be old, but it might be used recently, okay. In that case, if you are replacing that particular block, then again CPU will want that. Then again you have to bring that to main memory, right? So then obviously it may not perform well, right? Because it is ignoring the access pattern, okay. Whereas LRU is giving importance to the access pattern. It is not replacing the one which is accessed recently. It is replacing the one which is not accessed recently. Whereas FIFO says that you don't see all these things, just replace the oldest one. But in reality, FIFO not performs better than LRU, right? Okay. So there is a simplest algorithm which says that just replace any random block. It is neither FIFO nor LRU. Okay, whenever you want to replace, whenever you if the so the question of replacing comes only when the particular set in a cache is full or the entire cache is full, okay. So entire cache is full in case of full associative mapping, okay. In case of set associative mapping, if the particular set in a particular set, if all blocks are filled, okay, then the random algorithm just says that you don't go for LRU or anything, just replace the random block. You using a randomly, you select any block and replace that, okay. But actually this random replacement in practice, it is quite effective. It is quite effective. It may not be as effective as LRU, but it is reasonably effective. It is effective than FIFO. So this is quite interesting, right? Because in LRU also you have to maintain some counter, you have to increment, you have to decrement, and you have to identify. So that also involves cost, right? That also involves cost, right? But in random replacement, you are just randomly replacing, but it is quite effective, right? Okay, fine. So that's it about this particular topic. So in the replacement algorithm, so the main replacement algorithm we have discussed is LRU, least recently used algorithm, and the other things are FIFO and random replacement techniques. Fine, let us stop here. Thank you.